Hello, welcome back. So in this episode video, we'll be talking about how to go from a K-map to a Boolean expression. So to do that, we'll be doing something like creating groups. So what do I mean by groups? So in this um, Karnaugh map at the end of the page, you can see here, a group is a group of values that are the truth table's values of X or after the expression. So what are the requirements of our groups? Well, first thing is the groups must be rectangular, meaning they can't go like something like this. They must be a rectangle and not a diagonal. And then they must only contain ones, meaning that something like this isn't a valid group. They must have sizes of powers 2, meaning that they can only have sizes 1, 2, 4, and 8. Meaning something like this is not a valid group, even if they're all ones. And then the next criteria is that all the ones in the K-map must be in at least one group. Something to note that is that you can have a one that's in multiple groups, meaning it's in, for example, a group like this, a grouping like this is allowed, but it's not optimal. So to get the optimal grouping, we require the groups be as large as possible and there be as few groups as possible. And you'll see why in a second. So let's create groups for the graph, K-map below. So the first group is pretty obvious. We can just wrap these four values around and we have a group that meets the criteria of being a rectangle, contains only ones, has a size of 4, which is power 2. And now we need to cover the one on the left upper corner. So you might be inclined to just wrap it around this one. It fits all the criteria, but it's not the largest group possible. Remember in the last video about gray code, we talked about how the gray code is a circular sequence, meaning the last element and the first element differ by only 1 bit, which fits the gray code criteria. Therefore, we can create a grouping like so. We can just put these two ones together to get a bigger group of size 2, which still fits the criteria. Okay. The next step we do is we find the common variables in these groups. For example, in the red group, we can see that B is 1 in like B is 1 for the red group, and A and C changes, meaning A and C doesn't matter. So as long as B is true, the expression will evaluate to true. So for the red group, we just have B. Now for the black group, note that the variables that's not changing is A, which is constantly 0, and C, which is also constantly 0. So we write down A naught, C naught, connected with a dot, meaning and. And then the next step we do is connect the groups using an OR operator, which is a plus. So we can just do B or A naught and C naught. And this would give us the Boolean expression that corresponds to this Karnaugh map. You can test this on trying to convert this Boolean expression back into a truth table and then back into a Karnaugh map and see if they match. All right, let's look at a slightly more difficult example right here. You have everything you need to actually do this example, so I would recommend you to pause the video right now and try solving this example by yourself. And when you come back, I can show you the answer. All right, welcome back. So let's start by creating the groups as we did before. So one obvious group is these. Note that all the other blanks are just zeros. Sorry, I didn't mention that earlier. But okay, moving on. So that's one group. This is the second group. And once again, you might be inclined to just circle the last one as a one group. But remember, the gray code sequence is a circular sequence, meaning we can do something like this. This works because you can think of the gray code sequence as wrapping around as a ball. And when you wrap it around, these four ones will be connecting each other, making a rectangle that's the size of 4. Okay, so this will be the resulting grouping, and now we need to solve for the groupings. So let's get started. For the red or pink group, we notice that y doesn't change, it's always a 0, and x doesn't change, it's always a 0. So x naught, y naught. And then for the next group, let's work on the purple group. We notice that y is always a 1, and z is always a 0. And then you also note that w is always 0. So we have w naught, y, z naught. And then moving on to the green group, we note is that z doesn't change. It's always 0. And then x doesn't change. It's always 0 as well. So we have the final Boolean expression as x naught, y naught, or, oh, sorry, I need to put the dot as the AND operator. So x naught and y naught, or w naught, y, z naught, or x naught and z naught. Something to note in K-map simplification is that it's possible to have choices of how to pick the groups within a K-map while fitting all the criteria. As seen in the K-maps down below, you can see that they are the exact same mapping, and the grouping all fit the criteria. The groups are as large as possible, there's as few groupings as possible, and all the groupings fit the criteria of having sizes powers of 2, containing only ones, and being rectangular. And all ones are contained in at least one group. And when this happens, you need to realize that, in fact, all these groupings, the Boolean expressions that came from these groupings will be logically equivalent. Meaning you can use the 10 rules as we talked before, the absorption rule, the distribution rule, and etc., to go from one Boolean expression to another Boolean expression. And something else to note is that you can, since K-map simplification is another way from going from a truth table to a simplified Boolean expression, in an exam, you can use the K-map simplification to check answers for when you do the other form of simplification of going from a truth table to sum of products and then to a simplified form, or the other way around. You can use the sum of products form and the simplification to verify that your K-map simplification is correct. So yeah, that concludes this unit. I hope you had fun and you learned a lot. Yeah, let me know if you have any questions, and still have a great day.